Testing 1, 2. Don't kick the tripod there. All right, guys, so good morning once again. We don't have people that clean the rooms anymore. Because it's this place. What is that? But now, guys, simunga wana chat muli doti zona. Why are you poka? Leta kwa. Not just here. Okay, where did we end last time? Hello? What were we doing last time? Okay, so I think we talked about treatment processes, right, of water. And we talked a bit about design aspects of a sedimentation tank. Did we? And we had an example, right? And this example we talked about, I think you are given a surface overflow rate of a flocculator clarifier, and we say the sedimentation tank is a clarifier. Is also sometimes referred to as a flocculator. And it has a 60 liters per square meter per minute. Express this as a rate of that. So, did I give you some self-help questions to practice on your own? I didn't. Class rep, where are you? Saripo. Madam. Okay, let's try to do one good example, sort of a build-up from the last example that we talked about, or we calculated. Okay, so I like to think that we have the module. So let's just tackle the next example that is in the module there. So this problem, so by the module, it's introduced as problem 6-4, all right? So I'm going to dictate. Let's try to solve this. Hopefully we'll still have a bit of some time to just start a new topic altogether. All right, are we good? Calculate the diameter. Calculate the diameter. Calculate the diameter. And SWD, we talked what the SWD meant last time. Okay, calculate the diameter and the SWD. Of a settling tank. Of a settling tank. Settling. Of a settling tank. To treat a flow of 20 by 10 raised to the power 6 liters per day. Yeah. Of a settling tank to treat a flow of 20 by 10 to the power 6 liters per day. That is 20 million liters per day. If you want, you can write that, but it doesn't really matter. Full stop. The maximum SOR, we also talked about the SOR. What is the SOR? surface overflow rate here, taken as 18 cubic meter per square meter day. The maximum SOR is 18 cubic meter per square meter per day, and detention period denoted as T as 3 hours. Okay? All right. So let's try to see how we can solve this. So we solved one question last time we met. If we couple it with what we're doing now, the rest are just repeating questions. So you should be comfortable to solve other questions. Okay. So let's see how we can find a solution to this. So one, there are many units you can work with. But usually when it comes to the level at which we are, we always talk about the SI units, right? So if it's a liter, find a way of converting it to a cubic meter, because volume is ideally should be measured in cubic meters, and we know how to convert that. If you also have a day, well, a day is ideally okay. Mainly in engineering works, information is presented when you talk about time in days, so we can keep that. So the step number one you're going to work on is convert the volume that is coming in into a cubic meter per day. Are we together? All right. So we have a 20, which is the 20 million liters per day. You and I know that 1,000 liters will always give you 1 cubic meter, but then the day just remains the same, so we leave it at that point. If you calculate this well, it should give you a 20,000 cubic meters per day. But then, like I said, you can still, if you want to work with liters, but at the end of the day, if things are canceling out and then you're presenting the information with the right units, that's still fine. But this route has been chosen because it's one of the easiest routes you can ever take. Your next point is talk about detention time, all right? Detention periods, okay? But of course, this is time denoted as a T. Last time when we met, we said time is equal to what? Distance over speed, right? And from what we did, and this is just a build on, SOR, this is a rate. This already is speed. We did something like this the last time we met. So time is equal to distance over time. So that basic equation that we learned kapena mweza grade 5, 6, somewhere there, right? It still comes here. When you think about it, this is surface overflow rate. Rate is speed. Okay, so you have that. And then you're looking for that value. Or at least, can you find that value? SWD. SWD is just a distance. Okay? So essentially what you're dealing with is, from the top, of course, a clarifier will look something like that. And then it's got, that thing that just moves and then sweeps. So what they're asking you is, first of all, find the diameter of this guy. Okay? This is from the plan. From that angle view, if you're going to project down, this guy will just look something like this. And the side water depth, like we discussed, is just the depth. Okay, it's just the distance to which, from the base to how much we're traveling there. So let's put it as the side water depth. So these are the question marks that you want. Water supply in third year is mostly just you're trying to design. So you're given a few parameters that can work, then we're going to ask you to say, can you design a clarifier based on the flow that is coming, based on the velocity of water coming, based on the detention time. Okay, so time in this case should be distance, which is the SWD, side water depth, divided by SOR. And it's nothing that you even need to memorize, because this is just a basic equation that we've always known. Time will always be equal to distance over speed or velocity. Okay. Can we move on? Where have we lost someone? I'm seeing a lot of, I'm not too sure faces. On the what? On which one exactly? Okay. So whenever there is, we're dealing with a settling tank. And settling tanks are in different shapes, right? So it could be a rectangle, it could be a square, it could be circular. But whenever the question is going to say, find the diameter, then you know you're dealing with something circular, not so. You have seen the clarifier before? Yes. So from the top, this is what I've drawn here. So as a plan. So they are interested in you determining how big this settling tank should be by diameter, given these parameters that are coming in. But then does it just end there? They want you to find out how big it is in terms of diameter, but then to what depth can this guy also hold water, which is the side water depth. We talked about this the last time we met. So this is just a plan, and this is the, what view is this? What view is this? A house, you look at it from the top and then from the sides. We had those views that we used to. You guys use T-squares, and we had the plan. All right, so let's just maybe leave it. This is the plan, okay? Let's just leave it at the front. Orthographic view is it the one that sort of gives you the 3D, right? There's that's isometric. Anyway, we're digressing. Okay, here we are. So this is just the basic formula that we know. But then from this formula, we are trying to find the side water depth. So we make it a subject of the formula because we are good mathematicians. So can we multiply time by the side overflow rate? Okay, so you need this somewhere. Your time has been presented in hours. When you are calculating, or rather can I say the right units that you want to deal with, okay, are hours. Sorry, days. Because we are maintaining the flow as a day, so it means that we need to convert our time as well into a day. Are we together? So, like I said again, if you want, you can convert the days into hours, meaning you have to come and maintain the 3 hours here. If you're going to go by the day, then convert the time as well into a day. So it's up to you. That is not the only way you can skin a rat? Is it a snake or a rat? Okay, so there are many ways you can do it. Either you leave it in days, so come and convert your time in days as well. If you're going to leave it in hours, then leave this guy as hours. So in this case, since we have chosen our volume to be coming in as days, we need to convert what we are given as days. So, a 3 divided by a 24 by 18 will give you what? 2 point. I hope I haven't lost anyone here. We made this the subject time. And the time, since we can't work with it in hours, why? Because we've already begun working everything in days. So we're converting our 3 hours into what? Into days. This is just the fastest way to convert it into day. Then we are multiplying this by the SOR, which is the velocity, which is 18. So what you're having there is your first answer that you're getting as your side water depth. So your clarifier has this depth as a 2.25 meters. When you are solving, this solution hasn't in the module been illustrated, but this is what they want you to illustrate. Have a small sketch, come and show where the diameter is. This, even the marker knows that you know what you're talking about or what you're trying to do. So this was still under a question mark. Side water depth has been found easily as just getting there. So this, we're good to go. Okay? Okay. How can we find the diameter? I need to erase something. Okay, I think I need to stick here. Can I erase this part? Who would want to suggest how we can find our diameter? If you have the area, it's easy to get yourself a diameter, not so? Because for a circle, something which is circular, we always say that area is equal to what? Pi d squared over? So if you're going to make your diameter raised to the power 2 and then just make it the subject, then you'll be okay. But what we don't have is the area. So how do you get that? All right. So from this point, and I'm not introducing anything strange here. All the formulas that we've talked about so far, they have been a part of us since I don't know when, right? If this is the route that you want to take for you to come and find the diameter, so now the question is, how can I find the area of my clarifier? From this information, because we are very good mathematicians, I mean, we are engineers, we should be able to get our area from this one also. So, have you already done irrigation? Yes. So I would always say that discharge is always equal to what? Area by? Who remembers this? Hydraulics. Very much for me, it really sank in so much the time I was doing irrigation. This, you can never go wrong about it because what are the units for this guy? Let's say cubic meter per what? This should be equal to area is always equal to that. Velocity is equal to what? So Vapala 9. So this formula is a standard thing. Like as an engineer, it's not even supposed to alarm you. So based on what you're given, you can come up with this. Make A the subject. Velocity, you have it, don't you? What is the velocity? SOR, right? What is your Q? Chapwai. So you're going to get your A over here. So your discharge is a 20,000 divided by 18. So the reason why you are converting your liters into cubic meters. You remember what we did for us to get from the 20 million to a 20,000, right? It's because when you look at all the units that are dealing with what you want to cancel with, they need to align. So this value we convert it into a cubic meter per day. When you come to the SOR, it only has cubic meters, a square meter, and a day. So like these things are able to cancel each other out. But you cannot have a meter cube as volume unit measure. In the same value, there's also a liter. It won't work. So either you maintain the liter here and so come and deal with the cubic meter into a liter. You can do that. But then that's going to be tricky because this is also a problem. So the best way is convert, like join the winning team. There's so many M's here. It only makes sense that you convert the liter into M's as well. Does that make sense? So this allows you to do this and things will cancel each other out. All right? Your value, if you do that the right way, should be a 1111.11. What are the units? When you're solving all these, much as your goal is just to get to the diameter, all these are some points you can earn just in case you make a mistake at the end of the day. So don't just say A or area, you just leave it at without the units. For me, I'm going to think that maybe you're just copying this. So put the units as well. Flow with everything. Once you have that, that should be very much easy because you go back to this equation and just make this the subject. And I won't really take time here because you guys are good with this. So your value will be a 37.61 meters. You are the engineer. You are the consulting engineer. You cannot present this to the contractor. So you make a decision. Round this off to a value that is workable. That is, you can think about it, right? So it's up to you. You can say, so take it as, this is already into a whole figure. So just say 38 meters of a diameter. Any question? Where, what came from where? There hasn't been anything strange, has it? So this is your diameter, and you come back here, okay? And then so your diameter is 38 meters. The module hasn't made this sketch, but I would expect you, since you are designing, to also put in a sketch and show me where the diameter is and where the side water depth is, just so we have. Any questions? What is that? So, when you're designing, there are always what you call verifications or checks, okay? When you design something, there are certain values that need to fall under certain brackets. And if those values are not in that bracket, then you can say this structure won't work. In structure engineering, for instance, that is very common. A good number of engineers that have gone to do a master's level structural engineering, that's basically just what they do. So you are going to come as a designer, as an architect with a drawing, or an engineer. You're going to give it to me as someone with a master's with a stamp to verify buildings, that these buildings are safe or not. So I'll run through what you have put as the columns, as the pillars, as the materials, the distances between this and that, and verify that, okay, if you take this onto the ground, it won't collapse. Are we together? Which reminds me, you've heard about the society building in Lusaka, right? So why they are blaming engineers on that is that, yes, there will be someone to design, but there should be someone to specifically counter-check that each and every column that whoever designed is suggesting won't collapse or it won't develop any cracks. But if you're going to live in a society where you bypass certain, steps for something to be approved, those are the implications. Because everybody's been vacated, right? Imagine the number of people that have been inconvenienced, the number of businesses. So for engineers, we're not just dealing with one life. A doctor, you make a mistake on one person, they die, you recover in some way. But for engineers, you design that, it collapses. How many people will be in that building? So we take our profession very seriously, because first of all, the monies that they just put in there, the time they've put in, the inconveniencing that has just happened right now, it's just... So anyway, my point is we check a building for certain values. If this value is falling within the range, then we can certify that, okay, this clarifier works. Okay? So, the next point, can I erase this? So, ukutapeza mansa zai. But you go on further. Okay, so that's right. So just say checks. And then you say, if within acceptable limits. If within acceptable. Limits. And how do we check that our clarifier won't collapse or it's going to live up to what we think it will do? There's what we call a wear loading. Okay? A wear loading. This value is gotten by saying the Q that you are working with divided by the pi and the diameter that you found. So if your diameter was wrong, probably you want to verify it the right way. The Q we were already given. So you go on about to say your 20,000 sitting over here divided by 3.14 by your 38. And the answer that you're finding is equal to a 167.62 cubic meter. Okay? So if your wear loading is less than a certain value, then we say that the structure is safe. Okay? So this value is falling. So I can go on to say this value is less than a 250. Then you can deduce as the engineer to say, therefore, so you can say, hence, okay, or safe. But if you found that your wear loading was more than the 250, then you state that your structure is not fine, sir. And the designer should go back and just rework on the aspects. And how do you get your wear loading? The Q that you are given really comes in handy, but then you are working with the right units because your diameter is in meters, you kind of have a liter on top. A pi is a well-known value, and then the diameter is what you found. So, notice how the question initially never asked you to check, but you're expected, because you've been designing based on the factors given, to just check. It's just a normal thing to do. So, it could be a test, a quiz, or an exam. Whether I have said check or not, you need to check. Because if you don't check, then you are not designing at all. Yes, madam? Like the minimum it can go to, like a lower value. Well, in this case, it doesn't really matter how low it is. It could be even like 1 cubic meter per something, as long as it's less than a 250. So it doesn't matter how low that value is. Let it just not go beyond. What would you say if those values were the same? Is it safe or not? It's not safe, fine. So it should be less than. Yeah, everything that follows is just basically the same. So find time to go through so this will be just a practice question, and then I'll send you my assignment. So practice or exercise. This is problem. Yep, these problems look good. Just the next one. Problem 6 does what? Does 5. So just practice that, and see what you get. See if you can fully cement on what you already know. Okay? Any other questions based on this? I've really taken my time to explain this. If you're able to get the basics of this, then the rest is very much easy. Because with this class, this topic actually gets to be done. The next time we meet, we'll come and talk about, and so remind me, Okay, we'll come and talk about flocculation, coagulation of water. And in it, there are calculations, there are designing parameters that you need to consider for something to just be workable. One more thing I would like to bring to your attention is that this module always has very good questions at the end of each unit. So find time to just go through that. Why should water be treated? Write short notes on Stokes' law, hydraulic subsidence. All the answers are in the module. So ukafeluka course in Shuafuna Chabe. Okay. All right. Any other questions? Tomorrow, I want to be honest because I rarely lie. I'm not showing up. But on Friday, we need to meet. All right.